Hi all, Stuart here again. In today's video, we want to talk about moments of inertia. So this is a fairly tricky concept to describe physically, but mathematically it's quite similar to the first moments that we've discussed earlier in the last video. So this will be a fairly quick video. We're just going to go over the definition and then do some examples. And we should all be all set. All right. So here's just the definition for the moment of inertia. So let's say that I want to find the moment of inertia about the x-axis. In that case, I take the double integral over the domain of y times the density, of y squared times the density function. If I want to find the moment of inertia about the y-axis of the body, rigid body defined by the domain D, I take the integral of x squared times rho dA. And then finally, if I want the moment of inertia about the origin, or we call this the polar moment of inertia, you could, that is equal to the integral of x squared plus y squared times rho dA. Okay, so why don't we try an example for this? Should be fairly straightforward. Find all of the moments of inertia of, not odd, of a disk with a radius of a and a density of rho. So the density is going to be homogeneous. So what we're dealing with is a circle centered at the origin. Density is constant at rho. And we just have a circle like that with a radius of a. So we're keeping things all in variable form, which is fairly nice. Now we know that the polar moment of inertia, and sorry, I should mention, there's a property that says that the x moment of inertia plus the y moment of inertia is equal to the polar moment of inertia. So if I take I naught, so the double integral over the domain of x squared plus y squared rho dA, then what I'm going to want to do is transition this to polar coordinates. We're obviously taking this over a circle. So we get rho, we can bring that out, times the integral between 0 to 2 pi, times of the integral between 0 and a of r squared r d theta, because x squared plus y squared goes to r squared. What we get here, we can separate. So we get rho times the integral between 0 and 2 pi d theta, times the integral between 0 and a of r cubed dr, which is 1/2 pi rho a to the 4th power. Okay, so now again we use that ix plus iy is equal to I naught to determine that ix is equal to iy, which is equal to I naught over 2. And of course we say this because we're dealing with a circle, we can use symmetry. So we get I naught over 2 is equal to 1/4 pi rho a to the 4th. So that's moment of inertia, fairly easy to deal with. Now in the next video, we want to start talking about surface area. Now surface area is going to be something that's pretty important. It's the continuation, the natural multidimensional continuation of arc length that we did back in single variable calculus. So we'll talk about that in the next video. Thanks for watching.